Good morning. Good morning. Good morning, Soad. Hi, Daniela, and hi, good to see you. Don't think I didn't see. Anyway, I won't say it, but I know you were very, very first. Good morning, Vivian. Good morning, Alyssa. Good morning, Charlie. So I said, oh, and there's more. Okay, okay. Hold on. Okay. Yes. Good morning, Daniela. Good morning, Soad. Good morning, Alyssa. Good morning, Vivian. Good morning, Newell. Good morning, Charlie. I said that out of order, but I think that's everybody. All right. Good morning. Good morning. Let us do this. We're going to just totally continue with, oh, it's very dark. Sorry. I'm like in the, yes, it's physics in the shadows. Okay. But we are just going to totally, literally continue with where we were. I'm just going to continue with where I was 2 days ago. That is, I'm trying to wrap up this tilted Newton's law. Well, excuse me. I'm trying to wrap up and resolve the vectors for this Newton's law problem that involves a string on a tilt. And I'm going to try to cross apply that to the inclined plane problem that actually constitutes your final exam. Hopefully it's sort of clear where I'm doing. So I'm going to go right back to it. In fact, the notes here that we're going to, so yeah, the notes for today are actually going to, I don't know, it doesn't matter, but it's going to continue from the same PDF of notes as the other day. So I guess that doesn't affect you. Hold on. I'm just pausing for a second because this lighting is weird. I'm trying to see if maybe, let me see if I can improve the lighting for 1 second. Hold on, sorry. Maybe this will improve. I'm not sure. Maybe. Okay. Yeah. Ooh, that's odd. Okay. Okay. But okay. And obviously, please do stop me as we. Oh, more people coming. Okay. Once I get rolling, which I will in a minute here. Of course, stop me. Really stop me with questions, especially if you see anything I'm doing that in any way relates in your mind, to the practice exam document, or relates in your mind to lab 5 or something like that. Definitely do stop me. On the other hand, if I'm doing something and you're like, I don't see how this relates at all, then maybe hang on and wait, and I think you'll see how it relates. But okay, but so where we were. Right. This was our situation, right? Hopefully everybody's with me. Again, it's in the notes from Monday if you aren't with me, but the situation is the block on the table being pulled by a string that's on an angle. So we're ultimately trying to figure out the rate of acceleration of this block. We drew a system schema. We drew a pure free body diagram. And again, this is the sequence for how we solve any Newton's law problem, certainly including the ones in the final exam, in the ones in live 5. And let me say this now too. Up until this point, like this is what we do with any problem at all, including an inclined plane. You do the system schema, then you do the pure free body diagram. Then what always has to happen is that the forces in the pure free body diagram have to get resolved into vector components. That's always the next step. And now here's where, and again, this is very related to the final exam. How we break the forces into components involves a choice. There is invariably more than one way to resolve forces into components. More specifically, there's a decision that has to be made as to which forces get divided up into components. And this is a very important, this is where things branch now. And this is where in the final exam, you'll see that you're asked to solve the same problem 2 different ways. So the 2 different ways don't differ through this stage. Like they'll have the same system schema, they'll have the same pure free body diagram. But then the question, whenever we look at a complicated pure free body diagram, such as this one, the question that arises is which arrows, which vector are we going to break up into components? And that has to be thought of consciously. The answer is whichever arrow does not lie along a coordinate axis. So in other words, but what that means, and this is the stage, I'm emphasizing this because this is the thing that people often misunderstand or don't understand or get wrong or something. In order to decide which arrow to break up, what you really first have to do is consciously decide, what are my axes? Do they, for example, look like this, or do they look like that, for example? And there's other options as well. And so once you decide what your axes are, then any arrow that is not parallel to one of your axes is or any arrows, and there may be more than one, that's not parallel to one of your axes is the arrow that gets broken up. Okay, and again, let me emphasize, this is a choice for any given problem we do. You could make any decision about what your X and Y axes are going to look like. All decisions, if done correctly, should lead to the same correct answer, but some decisions will do so more conveniently or easily than others. No matter what, you have to make a consistent decision and stay with it. So the strategy in general, what we find in general is if we line up our x-axis, our positive x-axis, to be lined up with the expected direction of acceleration, then we will probably have the most convenient, easy time solving the problem. That is, if we do that, we'll have the fewest number of sines and cosines to deal with. We might even find ourselves breaking up strange or unexpected or multiple vectors, but we'll still have the fewest number of sines and cosines to deal with. So that's what's about to happen here, or what we started 2 days ago. But again, let me just emphasize that in the final exam, you are actually asked to do the inclined plane both ways. You're literally asked to try one at a time, 2 different coordinate systems. And you're trying to show in the final exam how no matter which coordinate system you do, you'll arrive at the same correct answer. But one of those coordinate systems is ultimately going to take less work than the other. That's what you're trying to see in the final exam. It is a comparison deliberately. Okay, but here I'm doing one way. All right, so what I did was I decided that I believe that this block or this box or whatever it is, this package that's on the ground. And again, please stop me if I know I just dove right in today. Please stop me if you don't know where I am or what I'm doing or why. But I'm doing the same problem from Monday. In this problem, I'm pulling it up on an angle, but I'm expecting that the package is going to accelerate horizontally along the floor. Therefore, I call that the expected axis, the horizontal axis, I call that the x-axis. And so anything that's not lying along that axis or the perpendicular y-axis gets broken up. In this case, that's tension. I zoom in on tension. I make tension the hypotenuse of its own right triangle. This goes back to just basic vector stuff, not basic, but fundamental vector stuff from displacements and velocities and all that. Whatever vector I'm breaking up becomes the hypotenuse of its own little right triangle. No matter what it looks like, it becomes the hypotenuse. And I get its legs. One leg is hypotenuse times sine. The other is hypotenuse times cosine. And it depends on where the angle is. So that's what I've done. Oh, sorry. So, okay, this just page from yesterday, from Monday, just says what I just said, that we have to choose wisely our x-axes and y-axis. Okay, that's just more, again, I'm just flipping through the pages from. But so then what I did on Monday here on this, and again, you know, if you weren't here Monday, whatever, this is all in the PDF of notes. It's posted from Monday. But now here I zoom in. Excuse me. I zoom in on the offender, meaning on the vector that was not along an x or y axis. And I zoom in on it as it is, like this tension vector was up and to the right. So I draw an angle from the horizontal. I always draw an angle measuring the vector from an imaginary reference horizontal line. I always do that. And so the adjacent to that angle is hypotenuse times cosine. The opposite to that angle is hypotenuse times sine. I mean, this is all SOHCAHTOA hidden. Okay, and thus I say from now on, okay, it's no longer tension then. It is a tension, it's a sine component of tension, pulling along one axis, and independently yet simultaneously the cosine component of tension pulling on the other axis. Please note, what are sine and cosine really? I mean, you get sine and cosine of the angle on your calculator, but what are they really? They're percentages. If you really, you might never ever thought of this before, but realize that sine, the value of sine is never greater than 1, right? Like the magnet, like plug in whatever angle you want into your calculator. And by the way, for this kind of thing, I'm in degree mode. You plug in any angle you want in degrees into your calculator, you'll never get us, and you press sine, you'll never get a value greater than 1 or a negative value less than -1. And similarly, with the same thing with cosine. In other words, the calculator is always going to spit out a fraction, a decimal. That tells you something. Hypotenuse times sine, what that really means is some fraction times the hypotenuse. The vertical component of tension is some fraction of the overall tension. The horizontal component of the tension is some fraction of the overall tension. The legs of a right triangle are always smaller than the hypotenuse. So what we're really saying in English is that when you pull a block up at some angle, if you pull it up and to the right, what you're really doing is you're pulling it some amount up and some amount right. Each one of those is a fraction of the overall pull that you're exerting. We're going to run numbers in a minute and see this, but the greater the sine, the greater the fraction of the greater the vertical fraction will be in this case. And the greater the angle, the greater the sine, and the greater the vertical fraction will be, but the smaller the horizontal fraction. Sine and cosine are just basically telling us how large is the portion of our force devoted to a particular job. The tension is doing 2 jobs. It's lifting the block up some amount, and it's lifting the block over some amount. Those some amounts is what we're figuring out with sine and cosine. All right, so we put those components into the FBD. This is where we left off Monday. And what we now have is a component free body diagram. Notice we went from a system schema that had 4 lines in it to a free body diagram that had 4 arrows in it. Then we chose our axes and realized that one of our 4 arrows was off axis. So we split it into 2 components because we're operating in 2 dimensions here. So that one arrow got taken out and we substitute for it 2 component arrows, the T sine and the T cosine. So we now have a final component free body diagram that has a total of 5 forces acting on an object. As far as we're concerned now, we're looking at a mass that has 5 influences acting on it. What do we do now? Now, finally, after all that, and that is, again, that is the actual hard work. That is actually the heavy lifting. It's probably harder to listen to in class because you probably, if you're like many people, you probably just want me to get to the numbers and the math already. It's harder to think about in an exam or on your own time because it feels like you're doing stupid things. I mean, or it did to me anyway. It feels like you're just like sketching around and like groping in the dark and like not really doing science. But I'm telling you that if you really understand all this diagram stuff that I just said, then you've really actually done the hard science and the hard setup, because now what we do Okay, now what we're going to do with these arrows is we're going to plug them into the left side of F net equals MA. These arrows are what we're going to put into the left side of F of sum of all the X equals MA, and thereby we're going to solve for A. Okay, and we're going to remember what it sort of said on the first page of notes today. F net equals MA is a vector equation. It really means sum of all of the F's along the x-axis equals m times a in the x-axis, and it independently yet simultaneously means sum of all the forces in the y-axis equals m times the acceleration of the y-axis. It's separate equations for the separate axes. So we're going to look, now we can look at one axis at a time. Now we finally can, because we did all that work and made sure that we only have forces happening on one axis at a time. Okay, so everything we're going to do here is about F net equals MA. the first question that we were asked, like there's like friction involved here and stuff like that. So before we're solving for A, we were asked, is there an A at all in the horizontal direction? In other words, is A even greater than 0? So I have to solve for that first. So I'm applying F net equals MA to the horizontal axis. In the horizontal axis, I have, oh, and I should have said, like, let's assume that this is the plus direction along the x-axis. This is the minus direction. Along the x-axis, this is the plus direction, and this is the minus direction. This is assuming, we've set it up. So this is our x-axis, and this is our y-axis, right? All right, so I'm looking at the x-axis. In the x-axis, I'm adding up all the forces in the x-axis. So apparently I have T cosine theta, that's a force, the horizontal component of tension is going one way, and I'm adding it to the friction, which is also in that axis, but the friction's going the other way. So I'm going to put a minus sign on the friction, right? So this is an F net equals MA statement for the x-axis. You see how in the left side, so the whole point of all this is expanding F net, sum of the F's. The whole math that happens is an expansion of the left side of F net equals MA. The right side is always just M times A. The left side is what gets expanded and gets complicated, and we only know what to put there because of these diagrams, right? So we have T cosine theta pulling to the right minus friction pointing to the left equals MA in the x-axis. Now, we don't even know if this thing is moving or someone's coming. So this is the stage, and are we recording? Yeah, we are. Okay. This is the stage where we're trying to find out if it's even moving. So this is the stage in our minds and sort of in reality, in time, like where static friction is trying to do everything it can to resist T cosine theta. Static friction will be as great as it, like if T cosine theta is nothing, then static friction doesn't have to do anything, and the block just sits there. If T cosine theta is like 1 Newton, then static friction will pull back with 1 Newton and hold the block in place. If T cosine theta goes to 2 Newtons, static friction goes to 2 Newtons and holds it in place. And you know this, by the way, I mean, I'm telling you, but you know this from life, because if you go over and try to move something, if you pull on it really lightly, it won't move at all. And then you pull a little bit more and it still won't move. You can test it yourself, but you pull it enough and then it moves, right? So this shows that there's a friction force in place that's not beating you all the time. It's matching you all the time. Static friction is tying, matching, equaling anything that's trying to slide one object relative to another. It will do whatever it can do to keep it there until it no longer can. It will exert itself all the way up to a maximum, at which point it loses the battle and the things slide and kinetic friction kicks in. So in other words, this is a battle between T cosine theta and static friction maximum. Like that's what we're really comparing here to see what's going on. If we're going to put in numbers in a moment, obviously, we're going to put in numbers in a moment. If this left side is anything greater than 0, the thing is going to move. i.e. if T cosine theta is greater than static friction maximum, the thing is going to move. But if it's less than 0, then it won't move. All right, so we got to start putting in numbers here. I'm just going to go to the next page. So I'm really asking, well, what is FS max? What's the max? I mean, this rhetorical question, I mean, you can answer it if you want, but the maximum amount that static friction can exert is the coefficient of static friction times the normal, right? That's not something, that's something you know, because I told you like last week. I mean, it's in the lecture notes and it's in a video. I mean, to be honest, I don't think we've used it together yet in lecture. We're using it now for the first time. Static friction maximum, just to remind you, I guess. 2 types of friction, 2 types of coefficients. Kinetic friction always equals the kinetic coefficient times the normal, and static friction is less than or equal to this is just the way friction works. We talked about this last week. Okay, so this is what I'm comparing. And by the way, please notice, of course, eventually this involves numbers. Notice that my habit always in physics, and it will be a particularly large habit in physics 204, I always postpone the numbers to the last possible step. I do as much physics as I can before doing any computation with numbers, because the numbers are just a detail that have to do with this particular example. First of all, the physics is the most important thing. Second of all, I don't want some little accidental math error that I make to like permeate and mess up all my physics all the way through. I want to make sure I've got the physics right. Then I plug in the numbers at the last possible minutes. And even if I did something wrong with the numbers, at least still the physics will be right. So I'm postponing numbers to the last minute. T cosine theta is, the question is it greater than or not mu times the normal? But now the question is, what is the normal force? Okay, notice in order to do what I'm doing right now, I'm looking at the horizontal axis. What is the normal force? Well, I don't know. In order to, there's no formula for it. There's no law that the normal force ever has to be anything. The way I know what the normal force is doing is I notice that the normal force is acting on the y-axis. In order to figure out what the normal force is doing, I've got to go to the y-axis and recognize that in the y-axis, definitely there's no acceleration. The block is neither flying up nor crashing through the floor. So all the vertical forces must be balanced in the y-axis. So to get the normal force, and this is always what goes on. Notice we did all this work with the vectors to break things up into 2 axes. The 2 axes occur simultaneously yet independently. It's very much like how the 2 axes, the y-axis and the x-axis, were independent yet simultaneous in that whole Wild Coyote Roadrunner problem that was on the midterm exam. Like, things are happening in one axis, things are happening in another. They're unified only in the sense that they're happening at the same time. So that's the one factor that is common to both of them. Here, what unifies the x-axis and the y-axis is that the squeeze that occurs along the y-axis is what causes the friction along the x-axis. Okay, but physics applies independently to each one. So I'm going to pause for a moment. In my look at the x-axis, I'm going to go over to the y-axis and say, okay, in the y-axis, the laws of physics are still holding. In the y-axis, the sum of all the y forces must equal the mass times the acceleration along the y-axis. I look back at my diagram. What's going on the y-axis? I'm just looking for a second. I look at the y-axis. I've got a normal force pointing up. I've got T sine pointing up, and I've got gravity pointing down. This goes back to something that a number of you were asking in direct chat and public chat on Monday. Like the normal force is helping out the vertical component of tension in order for them all to produce the acceleration of 0 with gravity. In other words, what I'm saying is this. So normal up plus sine component of tension up minus mg altogether equal ma on the y-axis. Now, what is a on the y-axis? No matter what's going on in this problem, no matter what's going on in this problem, whether we succeed in moving this thing or not, even if we move it, we're moving it along the x-axis, right? Even if we accelerate it, we're accelerating it along the x-axis. We chose the x-axis to line up with the direction of expected acceleration. Therefore, we can confidently say, and this is one of the reasons for the strategy, we can confidently say, aha, in the y-axis, there had better be no acceleration. And the truth, right? It's not, the block is not flying up or crashing through the floor, no matter what we're doing with it. And the truth is, even in the inclined plane, in the final exam, when we're solving problems, one of the reasons for this strategy of lining up the x-axis with the expected direction of acceleration is that therefore we can be confident that there's no acceleration in the y-axis. And that's actually extra information then. It means we can figure out things about the force, like F net equals ma. Ultimately, we're using all the F's in order to solve for A. But secretly, what's really happening in most Newton's law problems is we're using all the F's along the x-axis to solve for A along the x-axis, but we're getting some of those F's by first looking at the y-axis where we know the A to be 0. And from that, we infer forces like that. So all the information really matters. And it's really crucial that we've organized everything into axes. Otherwise, like none of this works. So I'm saying since A in the y-axis equals 0, that's information. That means the whole right side of this equation goes to 0. Therefore, I can say, okay, then n plus t sine theta, they together must be balancing the weight of the block, right? So notice the weight of the block is being supported by the upward push of the table plus the upward pull of the string. Together, they're supporting the weight. That's why I made that n arrow small, because I knew that the block was not being fully supported by the table. It's partly being supported by the upward pull of the string. Okay. Now, so this is a true statement. What are we solving for here? What do I care about? I care about n because n is going to determine friction. And again, honestly, this is why once you get in the habit of doing this and you follow what I'm doing, like for the inclined plane or like for the final exam, my suggestion, my strategy is to set up the axes the way I said. And then my general habit is I always solve for the y-axis first. I always solve for the axis I don't care about first. So I can get information about the normal force there. Then I use that information from the normal force to plug into the friction on the x-axis that I actually care about. And that is what we're doing here. So the normal force, in other words, must be the weight minus whatever help was being given to it from T sine theta, right? That's an expression for the normal force. I'm going to plug that back into the x-axis so I can get the friction. Like, this is not a final answer, but it's important. Plug. Okay, so the reason I did this is, again, friction sliding resistance comes from squeezing. The resistance, the push on one axis due to rough surfaces actually comes from, is results from the pushing together along the other axis. We've now gotten an expression for the pushing together. So I plug back in. And now looking at our values. Yeah, okay, this is correct, but I'm just going to move it over. Sorry. Oh, I'm sorry. I'll tell you what I'm doing. I made this mistake twice. I'm sorry. I kept changing my mind about the tension. Pardon me. Just this is a minor. All the physics is still right. I'm just changing one number because I did make it too crazy big. I said that I kept changing my mind. The tension. I'm going back to page 2 of this whole thing. Bear with me. I apologize. I'm changing one number. I made the tension way too big. I kept changing my mind about that. It says 500 here, but I apologize. Let's please go back and make it just 50. I made it too big for this problem to make any. Yeah, I made it too big for the problem to make any sense. Make the tension 50, okay? And so that doesn't change any of the physics. But this is another good reason why we're like, we just postpone the numbers to the final moments. They're just details. But so I made, please bear with, in fact, I'm just gonna pause for a second while I'm flipping the pages. Can you just confirm in the chat whether you just caught all I did? I made a mistake that I'm correcting. I'm changing the original value of tension from 500 to 50. It doesn't change any of the physics we've done so far, but it's just going to make this calculation possible. Now, can you just put in the chat if you follow? Got it. Thank you very much, Daniela. I totally appreciate it. Thank you, Charlie. Totally appreciate it. And remember, all of you can always submit for points for this kind of moment when it really does help. So thank you very much, Charlie, Daniela, Soad. Thank you very much. And who's Daniela, Charlie? So yes, thank you. And anybody else, and Alyssa, thank you. And it's not too late for anybody, even 2 minutes from now. If you were just writing something down and scrambling, but 2 minutes from now, you just want to put yes in the chat, it helps us all to know that we're all together. So, and I apologize. So I changed the tension. So it's not too late if anybody's still, anyway, I changed the tension to 50 newtons, which is what I should have done from the start. Okay, so now I'm just going back to the page. Sorry. Okay. So then the only thing that affects, so then here where there's a T on the page, I put in 50, our new value, okay. And notice, wherever I have G in any of these problems, and definitely do this on the final exam. I mean, wherever you see lowercase g is approximately 9.8 meters per second squared, but that is approximate as it is. So it's all to the good to approximate it as 10. That is not me like condescending to you or something. I mean, all physicists do that in contexts like this. So, and again, that's G. So if your mass is 3 kilograms, then your weight is 3 kilograms times approximately 10 meters per second squared, which means 30 newtons. Okay, so the weight pulling down on this block was 30 newtons. The component of tension pulling up was 25 newtons. So it's, you can see it's doing a lot of the work there. Like, yeah, like in effect, I mean, if you look at what we're doing, what we're saying is the normal force is only supporting 5 newtons of this thing's weight. The thing weighs 30 newtons, and newtons are, can be converted to pounds if you are more comfortable with that. But this thing weighs 30 newtons. The upward force of the table is only supporting 5 of those newtons of the weight because the string is pulling up and taking care of the other 25. So 30 minus 25 is 5. That's how hard the table is being. And so in other words, if you're following this, by the way, this means that the harder I was yanking on the string or the higher angle I yank on the string, the less friction is ultimately resulting. And by the way, also, that's why if you're trying to drag something across the floor, pulling up at an angle on it is a smart thing to do. It's a heck of a lot better than pushing from behind. If you pull up from the front rather than push down from behind, if you think about it, what you're doing is not only contributing to horizontal force, but you're also reducing the friction between the two surfaces. And that's what's happening here. So the maximum static friction is the coefficient of 0.7 times the 5 newtons. So the static friction coefficient is 3.5 newtons. Okay, that's the maximum. Sorry, that means static friction can be anything up to and including but no greater than 3.5 newtons, right? That's what this means. If we were, I'm just looking at the time. Okay, like, so if T cosine 30 was 1 Newton, or if we tried to pull this thing with 1 Newton, it wouldn't move at all because static friction would exert exactly 1 Newton. If we pulled with 2 Newtons, static friction would exert 2 Newtons. Again, this is not Newton's third law. There's no law that there always has to be friction or something, but if there is friction, this is how it works. If we want this thing to move, we've got to be yanking it horizontally with a greater force than 3.5 newtons. Are we? That's the question. What do we compare this to? What we've been saying in the prior pages, we're trying to compare US times the normal that we just figured out, FS max, which we just figured out to be 3.5 newtons. We're trying to compare that to T cosine theta, the horizontal component of the tension. That's right. So You see what I'm saying so far? And again, just to keep, well, okay, with this work, I want to summarize. We've in principle now answered the first important question. Like again, our ultimate goal in all these problems is to solve for acceleration. The idea is that once we get acceleration, then all the stuff that we spent all semester caring about kicks in, kicks in. Pardon me. So we're all trying to get acceleration, but once friction's involved, the real first question before you even get acceleration is there acceleration at all? Are we getting this thing moving? And in this case, with numbers, pardon me, someone's here. In this case, with these numbers, oh, apparently there is acceleration. Apparently we are getting this thing moving. We're not done with the whole problem, but we've answered the question, is it moving? Let me try to circle that or whatever. It is moving. How do I know? Because the fight in the x-axis was lost by static friction maximum. The net force in the horizontal axis outside of friction was greater than the maximum that static friction could handle in the x-axis. T cosine theta was greater than Fs max. T cosine theta was like 44 newtons, unless I did the math wrong, and stop me if I did. I don't think I did. I mean, I round it. I'm rounding to everything like to 2 digits just to keep it simple. But so the most that static friction could exert was 3.5 newtons. If I had exerted anything less than that, static friction would exactly match it and the thing would hold still. But I exerted with the rope, I pulled forward a lot more than 3.5 newtons. Please notice again, what we're really saying is you pulled up at an angle, we pulled by exerting a tension of 50 newtons. What all this trig and these vectors and everything are really saying is 50 got divided into 2 jobs, a rightward pulling job and an upward pulling job. It got divided in a triangular, trigonometric, vectory kind of way. What we're really saying here in effect is that 44 plus 5. Well, that's an odd coincidence, actually. Wait, sorry. Oh, no, sorry. We're saying 44 plus 25 equals 50. Let me say that again. In effect, like not in arithmetic, but in vectors in 2 dimensions, 44 plus 50. Sorry, 44 plus 25 equals 50. Right? If you pulled at an angle of 30 degrees with 50 newtons of force, that means 25 of your newtons went into pulling up and 44 of your newtons went into pulling over. Each one is a fraction of 50. The 2 add together, not arithmetically, but Pythagoreically, if that makes any sense. And that's why, but anyway, so the thing does move. It does move. A is greater than 0. Now, what is A? Is the final question of this question. And then when we get that answer, I'm going to show you how to relate this all to the inclined plane of your final exam. But the final question here is, so question 2, our final question was, okay, assuming that the thing does accelerate, at what rate does it accelerate? Now, you have to be a little bit careful here. We've done the hard work. What we're about to do is not going to be much harder. But now that we know what's moving, now that we've broken the static friction seal, the thing starts moving, but it's still rubbing along the surface. There's still friction acting. It's just not any longer static friction. It's now kinetic friction. So we have to be careful and use that coefficient now. So all right, so now it's all about kinetic friction. But we've done all this work. We have a straightforward F net equals MA problem. Like we have the F's, we're looking for the A. We're looking for the A in the X axis, right? So I'm going to apply, I'm going to do my analysis in the X axis. So now, okay, so now the friction is kinetic. Kinetic friction always is one thing. It's kinetic coefficient times the normal force. And the normal force is the normal force. It's whatever we put all of our work into figuring out already. It's just that the coefficient changes now. Like the normal force we got from y-axis. Okay, well, actually, okay, so the normal force, so it's very, also trying to say all the action ultimately, I mean, the results, the acceleration is all in the x-axis. And again, we intentionally chose the x-axis to line up with the acceleration. But the reason we care about all this information on the y-axis, because the y-axis invariably gives us the normal force. The normal force determines friction, and friction affects the x-axis. But whatever we got for the normal force is what we got for the normal force. The normal force, there's no formula for it. It will be different from problem to problem, but whatever it is in a problem, it is. It doesn't change from one type of friction to the other. Friction kinetic is mu kinetic times the normal, and friction static maximum equals coefficient static times the one and only normal. Okay, so I'm just going to go to the next page. I'm just going to recopy. I'm just recopying. So you notice, in other words, this is the exact statement I had pages and pages ago about the x-axis when we were looking at static friction. It's just that the details of static friction were different and the details of kinetic friction are not going to be different, but the overall statement is the same. right? And I'm postponing numbers for as long as possible. In fact, I'm going to postpone. So I'm saying, remember, I'm solving for, I'm solving for a sub x, the acceleration in the horizontal axis. So it's going to equal that whole, I'm just going to divide both sides by m now, and then I'll plug in numbers. T cosine theta minus mu k times mg. So I'm distributing the negative sign and I'm distributing the negative mu k, if that makes sense. I hope it does. Right? Like, so this is correct physics. And this looks starting to look complicated, right? This is not a thing you should memorize, this line here. This isn't like a formula or an equation. It's just a result of this particular problem. And it looks complicated, but it's just a bunch of numbers that I'm now finally going to plug in. Again, I'm postponing numbers because in case I did something weird with the numbers, at least all of this is right. And notice there's no more, I don't really mean to make the mu flying down there like that, sorry. But notice there's really no more there's really no more simplifying I can do at this point before plugging in the numbers, because, for example, I cannot cancel out the m's. You notice that there's an m in one of these terms, one of these factors has an m, but the other terms do not have an m in the numerator. So if I want, so I can't cancel out the m's. If I had wanted to cancel out the m's, I would have to factor out an m from the top, from all of the terms, and then cross out, but I can't do that. So the m's are not being canceled out here. And mu sub k, I believe, correct me if I'm wrong, here's an opportunity for points or whatever. I believe I said it was 0.4. I don't want to flip pages right now. Well, I kind of do, but if anybody can confirm or deny for me, I believe we made mu k 0.4. But if someone could look back at the original thing and tell me, that would be great. Anybody want to tell? All right. Whoa. I'm switching to approximate because once I'm doing cosines and sines of these things, I'm rounding, so it's approximate now. But so we said that's 44 minus. And before I'm going to check that just to make sure. Hold on one second. Yes. Okay. Okay. So first of all, I'm saying that's the answer, unless I made a check if I made a computation error or something here. But I'm saying the answer to the question, and this is the whole question that we were asking. And you know, we still have 20 minutes for me to try to now relate this back to inclined planes, but this is a hard problem. This is about as hard as it gets. I mean, inclined planes may be one touch slightly harder, but it's essentially all the same elements, just tilted. the ultimate answer here is our acceleration of this block along this horizontal surface was 42 meters per second squared. In order to get and it was an object on a rough surface being pulled at some angle. So this involved a number of forces. It involved an angle. It involved roughness or friction. A lot of factors being involved. But so it was just complicated enough to hopefully show you that we can do complicated things. We can do hard things, as the podcast goes. As long as we do this Newtonian procedure, you could throw in as many forces and factors as you want into the situation, and it would be more details, but it wouldn't require any different type of thought or any more sophisticated thought. The idea here is you draw a system schema to figure out what forces are acting. You draw a pure free body diagram to get the directions of those forces. You choose your axes then you resolve and divide up any force vectors that are not lying along axes, and then you're in a position to apply F net equals MA simultaneously yet independently to each axis, one at a time. And you'll note that the axes get in the same way that in the kinematics problem, the axes sort of get interrelated by virtue of their simultaneity. Like the unifying factor between two axes often in a kinematics problem is time. The unifying factor between two axes in a Newton's law problem really is mu, is the roughness. Roughness along one axis will combine with squeeze against the other axis in order to make friction. So put another way, the unifying factor between the two axes is really the normal force. You solve it in one axis in order to use it and apply it in the other axis. Okay, but this is the answer to this question. Now the question, and stop, well, what I want to do is I want to spend 18 minutes or so trying to more directly or explicitly apply this to the final exam thing. Are you guys, any questions before I go on, or can I get any either denial or confirmation? Are we okay? Is this clear? Sort of. Yeah, okay, cool. Okay is a fair word. I understand. I totally appreciate that Daniela's answer was not like, yes, awesome. It was like, okay, but fair enough. All right, fair enough. It's okay. I mean, and yes, you want to sit with this and let it sink in. But okay, no, I mean, LOL to me, but I totally appreciate the honor. Like, and look, all right, I'm going to go on. But one thing I learned also about physics somewhere along the way. No, okay, yeah, I'm totally not calling you. All right, I'm just going to move on. But no, I totally respect. Look, I respect the humility too. I mean, one thing it took me a long time to learn about physics classes is a lot of times in physics classes, what you're doing is trying to get down the stuff that you have to think about later. Anyway, all right, I'm just going to move on, but like respect. Okay. Oh, just looking in the chat. Oh, okay. Okay, let's say now we have a block on an incline sliding, let's say down. I believe, correct me if I'm wrong, in the final exam, I believe it's down, but in your lab, it's up and it's down. But let's imagine we have a block, but it doesn't make any difference really. On Also, I think this is the angle. I think this is the way it's drawn in your final exam document. If it, hopefully you get versatile enough that you hopefully all understand that I could draw this either way and all the physics is the same either way, but stop me if I drew it the other way in the test. And if this is confusing you, I can flip this right now. But anyway, we have a block on an inclined plane. A lot of the same. Oh, and also let me say, I understand that in your final exam document, it may not be talking about mu s. It might not be making a big deal about static friction. That's okay too. It may or may not in the real thing. I'll update you about that. But it's the same. We might just be jumping in right from the assumption that the thing is already sliding, and that's fine. But notice we got the same kind of factors are applying. We've got a known mass of m. We've got a known angle of theta. We've got known coefficients of friction, mu s and mu k, and maybe this one's more important. And here we don't even have anybody pulling on an angle or anything because we don't need to, because gravity is going to do something for us here. But the ultimate question, well, okay, the same ultimate question, whether or not we first have to establish whether there is enough to get the thing moving at all, assuming once it is actually moving, our ultimate question here is, at what rate does it accelerate down along the plane? That's our ultimate question here, right? Now we might want to get a number, just like we got a number in the other problem, but notice, please, again, how much of all the work I did before I even plugged in a number, right? The number was like the final detail. So all of this physics exists and can be done with or without the numbers. Like what we got an expression for A that was just like this long expression of A equals M times G times blah, 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 blah. And then for our final numerical moment, we plugged in the numbers into that expression. But that expression was correct, regardless of what the numbers might be. So I'm going to do the same thing here. I don't even care at this point, especially with limited time. I don't even remember in the final exam whether numbers are given or not. I am going to not care. I just want to solve this problem, know what to do with the M and the mu and the theta, just period, in order to find an A. Okay, so I'm going to go a little fast here. We got 12 minutes. I'm going to go a little fast, but I want to show you how the procedure for this lines up exactly with the procedure we just did a minute ago. And you might, like, God bless Daniela and everybody else, you might want to like think about the other procedure at home and let it sink in and practice with others. But I am hopefully you'll see that it makes sense. And this is only a minor twist on that. So what is the procedure? What am I saying? I'm saying first I'm going to do a system schema, like always. Okay. And but I'm not going to talk about it as much. I'm just going to do it because blah, blah, blah. All right. So system schema. So standard procedure. So here it is. Here is my system schema. Notice, just like the other one, only there's no string here because there's no string. There, right? There is no string touching it this time. And there's no hand or anything like that, because even if there might have once been a hand that flicked the thing up or something, it's no longer in the situation. I'm just watching as the thing slides down. So the Earth is pulling it, the center of Earth or the celestial Earth or whatever, or planet Earth or entire Earth is pulling it as always. And then the plane is a surface that's touching the surface of our block, and it's touching it in two ways. It's pushing it and it's rubbing it because it's a rough surface. So this is our system schema, exactly like the other one, but just actually simpler because there's no tension. That's my system schema. There's 3 lines in it, so there had better be 3 lines, 3 vector arrows in my free body diagram pure. So that's what's going to happen next. Okay, pure FBD. Now I'm assuming that this is a stage where the block happens to be sliding down. I believe that's what is the case in the final exam. So I'm going to say right now, if the block is sliding down, I believe that friction is resisting that slide, and I believe that friction is going to be pointing up. If ever a block were sliding up, then I think friction would be pointing down, like in lab 5. But here the block is sliding down. So here's my pure FBD. My pure FBD is we've got gravity pulling straight down at just like before. Now we've got the normal force. Oops. Okay, notice the plane is like this. So the plane, the plane, I totally cannot. Oh my God, I'm such a spaz. Okay, the plane is the way it's depicted in the diagram. So that means the plane is pushing up at an angle at the mass, right? What does normal force mean? It means in what direction is one surface pushing against the other, perpendicular to the plane of contact. So when the plane or the table was just purely horizontal, the normal pushed up. When the plane is purely horizontal, you can't even see this, the normal presses up. But as the plane is tilting, just think of the normal as like a little flagpole sticking perpendicularly out from the plane. As the plane tilts, the flagpole tilts. In other words, I'm trying to say that the normal force is like that. Yeah. Exactly, Daniela. That's awesome. Right. And in fact, it would be exactly 40. That's great. Like, for example, 45 degrees northwest, it's sort of like an up-west angle. And it would be exactly 45 degrees if the whole plane, if theta for the whole plane is 45, then this thing will be at 45. If theta is at 30, then this thing will be at 30 northwest. Exactly, right. And again, notice my normal does not equal my gravity necessarily. I don't see any reason why it should exactly equal the gravity because it's not even in the same axis. I think we're going to find out that the normal force supports a portion of the gravity. I think we're going to find out. I think it's smaller than, but either way, I don't think there's any reason to assume that's exactly equal. And then since the thing is sliding down, we've got friction pointing up along the plane of contact, along the slide, right? So this is my pure free body diagram. These are the vectors drawn in the direction that they're actually going. Also notice friction, whether it's static or kinetic, it's doing the same, it's doing that direction. The purpose of this diagram is to get the directions and comparative magnitudes correct. So now I've got these 3 arrows. It's actually simpler than the problem I prepped you with, right? In a way. So just 3 arrows. Now, that's the pure free body diagram. By the way, also, since we have 6 minutes, in terms of the final exam, that pure free body diagram is the same no matter what on the inclined plane. But now what happens is I see that not all of my arrows are parallel or perpendicular to each other. Some arrows are flying in different directions. Now I've got to make a choice. And the final exam actually asks you to try out both possible reasonable choices. We're not going to have time to do both of them today, but I can, finish on Monday. We still have class Monday. Tell me if I'm wrong, but I'm going to do one of the choices today. Like we have to break up some vectors. We have to break up some vectors in order to know which. Okay, good. Yes. And I totally agree with Danielle. That's awesome. Yes. And let me say this to everybody. Yes. Like some vector has to get broken up. And it is a choice. The way we make the choice is to decide what our X and Y axis are. Now, when you first saw this in lab, you might have been surprised, or maybe you didn't even know you were surprised. You might have been confused for reasons that you didn't even know. I'm looking at this picture and I see F as a diagonal line and I see normal as a diagonal line. I might think to myself, well, just like in the other problem, like they're diagonal, why don't I break them up into a straight up and down and a left and right? In other words, I might tacitly think, I'm used to axes, I'm used to x-axes that look like that and y-axes that look like that. And if I think of axes like that, horizontal and vertical, F and N would be weird, and I'd have to break them up. And in fact, we can do that, and it will get the right answer. But it turns out that if we do that, it will actually, even though it seems natural at first to say, oh, gravity's fine, it's just pulling straight down. It's friction and normal that are weird, just like in the other problem. It seems natural to do that, and we could do it. But it will end up causing a lot of work, as you attempt to show in the final exam. It'll end up causing a lot of work because the acceleration is not along this axis or that axis. We know on this inclined plane, the thing is going to slide down at an angle. So if we break those up, we're going to, first of all, we're going to have to break up two things instead of one. That's annoying. That's a lot of sines and cosines right there. And then the acceleration itself is going to have sines and cosines. So it actually turns out to be a lot of work, as you show and do on the final exam. So what's more straightforward, the reason we did what we did in the lab, even though you might not have fully felt comfortable with this at the time, what we do as physicists is we say, let's choose our axes. And I know we have like 4 minutes, but choose axes consciously and carefully. The strategy is line up X positive with A positive. So we're going to call, we're going to say this is X, and therefore this is Y. We're going to tilt the axes, which is what was happening in the lab. And therefore, if we tilt the axes, then MG becomes the offender. MG, it doesn't look like it because it looks straight up and down, but actually, if in this axis, if we're choosing to line up our axis or x-axis with the expected line of acceleration, then mg is the offender. And if I quickly in 2 minutes, if I then zoom in on mg and break it up, in this part you're going to have to, I'll say more about this on Monday, probably, hopefully, but you might have to give this some thought. But if I zoom in on mg and say to pull down is really to pull somewhat along the plane and somewhat in the plane. Notice what I'm doing here is a little bit exotic. I'm making mg the hypotenuse of a right triangle, and I'm dividing in, and this is what Daniela said, and she's correct. I'm making mg the hypotenuse and saying it has two legs, a leg along the x-axis and a leg along the y-axis. By pulling down, gravity, the weight of the object is pulling somewhat along the plane and somewhat into or against the plane, right? By pulling down, it's really pulling somewhat down left and somewhat down right. If you think about what I'm saying, it's got these two legs. So one of them is mg sine theta, and one of them is, in other words, one of them is hypotenuse times sine, and one of them is hypotenuse times, oh, sorry, I didn't mean to do that. I just messed up my whole thing, sorry. One of them is mg sine and the other is mg cosine. One of them is opposite the angle, the other is adjacent to the angle. That's the part you may have to think about a little bit. You might, and I could say more about this Monday, you might have to think about in your own private Idaho how I knew to put theta down here. I'm not going to spend time talking about that right now. But I will, well, this is the 1 minute. Okay. One fast thing I could say about the hardest part about this is how do you know which one is sine and which one's cosine? One thing I can say right now to help is remember always that sine of 0 is 0. Sine of 0 is 0. Cosine of 0 is not. Cosine of 0 is 1, right? But sine of 0 is 0. So, and the bigger the angle, the bigger the sine. So I'm really saying that the steeper the angle of this, the more gravity is pulling. The steeper the angle, the more gravity is contributing to to sliding along the plane. If there were no angle at all, gravity would not be shoving the thing along the plane. If the angle were zero, mg sine theta would be zero. There'd be no parallel component of gravity. But the bigger the plane angle is, the bigger the slide along the plane is. So that's why the along the plane side gets sine rather than cosine, because sine does that. Sine gets bigger as the angle gets bigger. That's one way of understanding it. There's others as well. But anyway, that's what. So since we have 1 minute, I now take these two components and I substitute and make a component free body diagram. That was the zoom in. And this is where we're going to stop here today. But this is the hard part. The component free body diagram looks then like this: normal, friction, mg sine, and mg cosine. And I don't mean to imply that they're all equal. I do. Well, this is the diagram. We're going to stop here for right now. But notice I went from a system schema of 3 lines to a pure free body diagram of 3 lines. Then I noticed that one of the 3 arrows, I noticed that one of those arrows was off axis. So I divided into 2 components, a sine and cosine. So now I have a final component FBD of 4 arrows. Then we're just going to do F net equals MA along each axis. We're going to say that normal must equal mg cosine theta to make an acceleration of 0. And therefore use that normal in the x-axis to say that normal times coefficient of friction minus mg sine theta equals acceleration on that axis. But I'm going to stop there for now. We'll finish this on Monday, but that's it. Hopefully you're seeing it's just like the other problem. But okay. Oh, sorry. Yeah, sorry. I thought I posted this. Yes, assume that I will put this in the Google Classroom, but I will post the final Tuesday night. That's a week from yesterday. So that's the 14th. I'll put it in Google Classroom, but I will post the final December 14th. You'll have until the following Sunday, the 12th, to turn it in. Okay, I will put that in Google Classroom, but it'll be posted Tuesday the 14th. It'll be due back Sunday midnight, the 12th. Does that, and Daniel, could you just tell, is that clear, or does that okay, great. Thank you. Okay, and I will put that in the classroom, but yes. All right, so I will see you.
Wait, sorry, you said it's due the 14th, and it's going to be posted the 14th and due the 12th?
I'm just sorry. You're right. That's crazy. I'm sorry. I didn't mean to say that. You're totally right. I mean, thank you. Sorry. Oh my God, that's so weird. No, I'm sorry. I mean, it'll be posted Tuesday the 14th and then due back Sunday the 19th. Like it'll be due back in 5 days. Like it'll be posted Tuesday. It'll be posted a week from yesterday. And then you'll have till the following Sunday night at midnight to turn it in. So it'll be posted, sorry. It'll be posted Tuesday the 14th by around 8:00 p.m. And you'll have till midnight Sunday the 19th to turn it in. I mean, thank you for that correction, but does that make sense? Oh yeah, okay, all right, cool. But thank you for catching me. Yeah, I did not mean that you, yeah, okay, cool. So are we all good? And again, it'll look, all of y'all, it'll look very much like the document that's in your classroom. So if you're doing anything from now to then, I would suggest just try to, with each other, try to work through that document in the classroom. I think it'll be a lot easier now that we've done this. It may still not be a joke, but you certainly have all the concepts you need to do it now, for sure. It's just a matter of us practice. But okay, but thank you guys. But you guys can go. I'm not waiting. I mean, don't wait for me. I'm just waiting to see if there's any other questions. But thank you. Yes, thank you. Have a great